The day I published this video on the German channel was the 100th anniversary of the discovery of rhenium. But what's so special about that? Before the discovery of rhenium, the periodic table looked something like this. Actually, most of them still had this structure, but I find this version much easier to read. As you can see, the 7th subgroup of manganese is completely empty. So the task was to find element 43 and element number 75. The first person to achieve this to some extent was Masataka Ogawa. He isolated a new element with a manganese-like chemistry from the thorium-containing oxide thorionite. Thorionite is essentially the pitch blender equivalent but for thorium. I will not dissolve this specimen as this will result in a pile of radioactive waste, and there is a problem with his data. Even though he discovered a manganese group element, it was not element number 43 as he has claimed, but element number 75. And as I said, he misinterpreted the results of his X-ray plate. He designated the new element as being element number 43 and gave it the name Niobium, but it was element number 75. The first isolation and correct interpretation was achieved in 1925 by Walter Noddack, Ida Eva Tacke and Otto Berg. Rhenium was isolated from the mineral columbite. Columbite is a niobium containing mineral. According to the records, they probably had columbite that was quite rich in manganese. However, they searched for this still unknown element not only in columbite, but also in platinum ores from the Ural Mountains in Russia. But why? We are familiar with these 6 platinum group metals from chemistry. If we expand this group like this, we have the classic, and if I expand it a little bit more, we have the elements contained in platinum ore. And there are the elements that can be found in columbite. We can see that it's obvious why the element was stored in platinum ores and columbite. For group 7 there was only one data point and manganese occurs in both. Today as then there was one problem. Platinum ore is not that easy to obtain. But here I have obtained some enriched coltan from our geos. Enriched means that much of the non-coltan, i.e. other rock phases, has been separated out. Coltan is a niobium tantalum ore. Columbite and tantalite form a mixed crystal series. The minerals and the elements they contain are quite similar. And I'm kindly allowed to use this to show you what the process behind the discovery of rhenium looked like. Because there's one problem with coltan, columbite, tantalite, tantalum, niobium and all that stuff on the left side of the transition metals. They are not attacked by conventional acids such as concentrated hot nitric acid. With a mixture of hot nitric and hydrofluoric acids, these parts can be isolated with the formation of negative fluoride complexes. But there's also one other possibility. For this purpose, 30 grams of the powder was boiled with 60 grams of sodium hydroxide and 15 grams of sodium nitrate. Over the flame, a melt of sodium hydroxide and sodium nitrate is created in this porcelain crucible. Molten sodium hydroxide also breaks down many things. A classical soda extraction is made with sodium carbonate, but they worked with sodium hydroxide. So what is happening here? What happens exactly in the melt is quite chaotic. To put it simply, coltan and columbite initially contain a fairly chemically inert niobium oxide matrix. Melting it in sodium hydroxide allows the lattice to be partially broken down. The broken lattice, where niobates and tantalates are present in a melt, makes it much easier to extract other enclosed elements. The elements contained are also present in the form of some hydroxide complexes, some kind of hydroxo-oxo stuff. Sodium nitrate helps as an oxidizing agent in the digestion process. What we see here, for example, is a very dominant turquoise color from manganate ions. The whole mixture was boiled for 2 hours and then left to cool down over the lunch break. This cooled melt can be returned to the nuclear chemistry as a finely ground powder. This is still a very basic mass, consisting mainly of sodium hydroxide, and it can be leached out with water. The following happens here. We have a very alkaline solution that continues to stabilize the manganate, which is why we have such a green-blue solution. The sodium salts of the niobates and tantalates formed are not very soluble in sodium hydroxide solution. The other elements, which were previously present as oxide or similar, either form water-soluble acids or do not and precipitate as oxides, hydroxide and hydrated oxides. Iron does not form any acids and precipitates as hydroxide. All the lanthanides also precipitate as hydroxide. Titanium, for example, precipitates as a sodium titanate and zirconium also precipitates. Niobic acid and tantalite acid exist and can also be produced by acidifying the solution, but they are present as niobate and tantalite here. So manganese remains in solution, as we can clearly see. Rhenium is also present along with a bunch of other elements in trace amounts. After filtering, we can see a red residue. This could be explained by iron 3, but that's only a guess. And there's also an extremely large amount of coltan still left. Yes, a few porcelain shards are also there, but we have broken down about 5 grams of the original 30 grams by boiling it for 2 hours in an oxidizing sodium hydroxide melt, just to show you how inert coltan is. The manganese was precipitated and separated by just adding hydrogen peroxide. The problem here was the manganese 2 can theoretically be oxidized to manganese 4 by peroxide and thus effectively precipitated as manganese dioxide, but we have the manganate ion in alkaline solution. This is generally speaking only semi-stable, and while I was preparing further off-camera stuff, the manganate had since long turned into the manganese dioxide, so I didn't even had to use peroxide solution. This alkaline oxidizing solution is then mixed with sodium sulfite to precipitate out residues of lead, bismuth, zinc and tin. We can see how the solution gradually becomes darker. This deep black suspension is then filtered, and I will keep both of them. Yes, I know there should be a clamp, but I hardly had any space with such large batches. So now we have a filter cake of the alkaline precipitated sulfites. Mrs. Tacke writes that uranium is still present and we can check this quite easily. Now I can simply measure the filtrate with the radio code 103G and display a spectrum. Except this filtrate is not active enough because I didn't use kilograms amounts of coltan. But we can see that the original material definitely had some uranium in it. The solution is then acidified and there was still enough sulfite in it to do another precipitation. However, toxic hydrogen sulfide is also formed. Vanadium, molybdenum, tungsten, arsenic, antimony, tin and germanium, for example, should then precipitate out in acidified sulfide solution. We can see how a cream-colored flaky precipitate is now forming. This is then made alkaline again with caustic soda and then drained off yet again. The remaining solution was then also completely evaporated until a salt crust formed, which then could be dissolved in concentrated hydrochloric acid. Evaporate, dissolve again, you get it. Until some sulfide could also be precipitated from the hydrochloric acid solution again. This sulfide residue were then measured with XRF. Unfortunately, the L-alpha line at 8.6 kiloelectron volts overlaps with the K-alpha line of zinc, which is also at 8.6 kiloelectron volts. This means that this line is not clear evidence for us that I have actually isolated rhenium. I have more zinc than anything else in the sulfides. But this video wasn't about isolating rhenium. It was just about bringing the paper, which had been published 100 years ago, to life with some observations. But I did use coltan, which contains rhenium, so why can't I detect any? I used 30 grams. Originally 1 kilogram was used and 0.05 to 0.5 milligrams of rhenium could be isolated from this 1 kilogram. So I would have had a measly 1.5 to 15 micrograms in there. I can't even weigh that on these scales. This is what 0.5 milligrams of rhenium looks like as ammonium perrhenate. And even this amount is subject to large measurement uncertainties. However, it must be said that Ms. Tacke believed that she had also successfully isolated both Eka manganese elements. She therefore proposed the name masurium for element number 43 and rhenium for element 75. However, element number 43, which we now know as technetium, could never be isolated from the ore using the methods available at the time, even though it is still present in tiny traces naturally occurring, but I will save that story for another time. This video was made possible by the Inorganic Chemistry and Nuclear Chemistry laboratories at the University of Cologne, and special thanks to Professor Dr. Gregor Stab, who made the XRF measurement possible, and also to the staff of the Geomuseum in Cologne, who provided me with the mineral for extraction, and as well, of course, to my Patreons for their financial support. With that being said, thank you for your attention and goodbye.